Here we go. So it is my pleasure to have Simone Brugiapaglia here to speak in the One World Mind seminar this Thursday. Simone is an assistant professor in the Mathematics and Statistics Department at Concordia University in Montreal. He's an expert in sparse and high-dimensional function approximation, and has a book, I understand, that will be coming out at some point in the nearest future with Ben Adcock, who I believe is also in the audience, and Clayton Webster on sparse polynomial approximation of high-dimensional functions. And presumably that also has something to do with the talk that he'll be giving today. So I'll turn things over to Simone and we can find out for sure.
Yeah, that's correct. Thank you very much, Mark, for the kind introduction. And I would like to thank all the organizers and Mark particularly for the invitation to this wonderful seminar. So before I start, let me acknowledge that this is work in joint collaboration with 5 wonderful collaborators: Ben Adcock, Cassie Bao, Nick Dexter, Sebastian Moraga, and Clayton Webster. Ben is a professor at SFU. Cassie Bao, at the time of the research I was presenting, was a SFU student, and then she went to UBC. Nick Dexter is a postdoctoral fellow at SFU, and Sebastian is a grad student at SFU. Clayton Webster is a professor at University of Texas. So this video is likely to go on YouTube. So like every good YouTube video, it should start with, okay, it already crashed. Okay, no, good. It should start with an ad. So as Mark was already mentioning, most of the material we'll be presenting today will appear in the following book that is under preparation with Ben Adcock and Clayton Webster on sparse polynomial approximation of high-dimensional function. So we already have a preliminary version available. If you're interested in taking a look and would like to give us some feedback, we'll be really, really happy to do this. So please write me an email. The second ad is about a postdoc opening in my group. So if you're looking for postdocs and you are interested in the research I'm doing, there is this opportunity within the Horizon Postdoctoral Fellowship Program at Concordia with start date before March 2022. I'm still considering candidates, so please send me an email if you're interested. All right, so yeah, there's some problem with my switch. I hope you can see it. Okay, it goes a bit slow. So today we're going to talk about high-dimensional approximation. So our goal will be to approximate a multivariate function, f of d variables, where d is usually a large number or possibly an infinite number. And we would like to approximate this function from some pointwise observations, or sometimes called snapshots. This is motivated by studying so-called parametric input-output models, and this is a ubiquitous task in computational mathematics and data science. Usually you have describing a certain physical phenomenon that with a certain model that could be a black box or a gray box. Maybe you know certain features explicitly of the model, and this model depends on certain input parameters that shape the behavior of the physical system, and then they give some output. This might be the solution to a differential equation, or maybe a quantity of interest. And this is a pretty general framework that includes applications in many, many fields, including weather or climate science, epidemiologic simulation. We know how important this is nowadays, and many other applications here. This has been the problem of interest in the field of uncertainty quantification, particular in the past years. And here's a suggested reading if you want to know more about real world and possibly large scale applications of uncertainty quantification. It's a pretty nice book about application aspects from Professor Ralph Schmidt in North Carolina. And so this problem that I described here in pretty general terms usually presents 4 main challenges. First, if you're modeling a complex physical system, then the number of parameters that you need to include in your model will be usually pretty high and possibly infinite dimensional. Maybe if your model depends on some function or on some infinite expansion. Moreover, collecting data or generating data can be expensive. It might depend on some physical experiments or on some costly numerical simulations, for example. Another challenge is that every data collection process is affected by unknown errors. And this is an aspect that I will be discussing in detail in this seminar. For example, you might have physical errors related to the measurements that you are doing with your device, or discretization error, numerical errors if you're dealing with simulations. And fourth, you might also have the case where the output of the model is infinite dimensional as well. So it might be high or even infinite dimensional. Your output might be living in a Banach or a Hilbert space. So just to make this discussion more concrete, let's take a look at this following example. So I still have problems with my slides. Okay, now I see it. The so-called parametric diffusion equation problem. This is widely studied in the uncertainty quantification community. It's a simple, I would say, toy problem that illustrates these four challenges. So some people also call this the cookies in the oven problem, because you could think, so here we have a two-dimensional physical domain that is a square. You might think of these circular subdomains as your cookies, and you're heating these, you're cooking them by heating the oven with, for example, a heat source at the center of the oven that is coming from this square. And then you can describe this diffusion process with a differential equation, with a partial differential equation, and the fact that each cookie might have like a different diffusion coefficient, like maybe you're using more chocolate and some cookie and some other material in others. So heat propagates in a different way depending on the region of your physical domain. So you can describe this with a parametric diffusion coefficient in the equation that is going to be piecewise constant in the spatial variable x, describing the position in the physical domain, and for example might have an affine dependence in the parametric variable y. So here you might solve this problem, and you might be interested in approximating the whole parametric solution map. So the map that brings you from the design parameters y to the solution to the PDE. And in this case, your solution will live in some Sobolev space, for example, H01, if you are computing a weak solution. Or you might be interested in some scalar quantities of interest, for example. You might want to know what is the integral of the solution over the whole domain, or maybe you're interested at maybe the temperature of the oven at a particular point. So you want a pointwise evaluation of the solution at a physical point. And here again, so this is for example, here we have 8 inclusions, so an 8-dimensional model, but you might have a more complex type of parametric dependence with many more parameters. In this case, data collection depends on the simulation. So you will have discretization error depending on how you are meshing the square domain here at different levels of accuracy, and which numerical PDE solver you're using. And of course, the output might be a function if you want to reconstruct the whole parametric solution now.
Can I ask a simple question?
Yeah.
The way that you have done it with x and y, there is no reason for me to think of x and y as any different. What do you have in mind when you separate the y and say y I will think of as a separate parametric?
Yeah, thank you for
the way that you do the cookies, the x's and the y's look very much the same.
So yeah, here, thank you for the question. So x is really the physical variable. So you see, I'm differentiating in x. There's no differential equation in y.
I understand.
So the differential equation is only in the physical variable, and I give you an instance of the parameters y. Then you solve the partial differential equation in x for that particular instance of the parameters. You compute the solution, and then this gives you the solution.
Okay.
Now.
Yeah.
There's no differential operator in y.
Yeah, so this is more like, it's just the picture that is a little bit confusing. If you told me that I have a parameter and I change the parameter and you didn't have the y direction look like the x, I wouldn't have interrupted you.
Okay.
Yeah,
Okay,
thanks.
sorry if this was causing some confusion. Okay, hopefully this is clear now. Okay, so in this talk, the focus will be on these 4 challenges for high-dimensional problems and how these 4 challenges can be substantially overcome thanks to the blessings of 2 tools, sparsity and Monte Carlo sampling. In particular, we will be interested in sparsity with respect to polynomial basis, in particular orthogonal polynomial basis. And Monte Carlo sampling, we will be just sampling our parametric model using IID random samples. So the talk will go as following. First, I will introduce some essential notions of sparse polynomial approximation. Then I will describe a setting on how to perform sparse polynomial approximation via compressed sensing and some of the recent theoretical results, that theoretical guarantees for this kind of methods. And then we will see with a little bit of detour how the ideas behind sparse polynomial approximation via compressed sensing can be useful to prove a so-called practical existence theorem for deep neural network approximation. And I will outline some open problems and opportunities for future research. So disclaimer, this will be mostly a theoretical talk. There will be a few numerical experiments discussed, but really at a minimal level. So mostly I will talk about theoretical guarantees. Okay, so let's start with sparse polynomial approximation essentials. So in the parametric domain, we will assume for simplicity to be in a tensor product type domain. So we are in a hypercube, -1, 1 to the d, and we consider a polynomial basis over this domain. So we'll consider tensorized orthogonal polynomials. For example, Legendre or Chebyshev polynomials. And their tensorizations will be orthogonal with respect to a certain tensor product measure. For example, in the Legendre polynomial case, you have the uniform measure on the hypercube. In the Chebyshev case, you have the Chebyshev or arc-sin measure in the hypercube. And this tensorized orthogonal polynomials are classically employed in approximation theory. And there's a lot of nice mathematics done about them. So there, if you're not very familiar with them, just think about them as kind of a Fourier basis. They're highly oscillatory. So, and the higher their degree, the higher the frequency of oscillation. So they form, they have really nice properties. Particularly, they form an orthonormal basis for the space L2 with respect to this orthogonality measure rho. And so we can consider an expansion, an infinite expansion of our function with respect to this orthogonal polynomial family, where we could in principle even compute the coefficients via integrals. Now, why polynomial approximation, the orthogonal polynomials is effective in this context? Because if your function is smooth enough, then you can prove that you have a really fast decay of the polynomial coefficients. More precisely, let's consider the so-called Bernstein ellipse. That is, again, another classical object in approximation theory. And since we are in multiple dimensions, let's consider a Bernstein polyellipse that lives in a d-dimensional space. So if your function f admits a holomorphic extension into to a Bernstein polyellipse of parameter rho, where this parameter describes the size of the elliptic region, then there are precise coefficient bounds available in the literature. In particular, you can show that the decay rate with respect to the polynomial multi-index nu is exponential, goes exponentially to 0, where the base of the exponent is exactly the sizes of this polyellipse. And also this assumption is not totally abstract. Actually, it holds for a large class of parametric models, particular parametric differential equations. This includes the parametric diffusion equation that I was illustrating before, or for example, the parametric harmonic oscillator, or time-dependent equations like a heat equation or other classes of problems. There is a pretty good amount of literature studying the and showing the holomorphic dependence of the solution on the parameters for a large class of models. So we have this approximation. We know that polynomial approximation, the polynomial expansion, we know that the coefficients decay very fast if your function is holomorphic. So we would like to consider a sparse approximation, an S-term approximation. We would like to keep only S terms in this expansion and essentially neglect all the others. The key question is now, how do we choose the multi-index set S realizing this S-term approximation? There are many possible multi-index set choices that are studied in the polynomial approximation literature. For example, you might consider a tensor product multi-index set, a total degree multi-index set, hyperbolic cross multi-index set. So if we were in one dimension, this choice would be trivial, because thanks to the decay, you know that the first S polynomials would be the most important ones. However, in multiple dimensions, we have all these degrees of freedom, and it's not clear a priori how we should truncate our expansion. So luckily, there is a theoretically optimal way to deal with this, which is the best S-term approximation. You can just pick the S largest coefficients of your expansion, because, for example, here I'm plotting the coefficients of an 8-dimensional holomorphic function. If you order the coefficients in the lexicographic way, you don't have any good pattern, and it's not clear where to truncate. But if you sort them in a non-increasing rearrangement way, then you know that, first of all, you can observe this really fast decay in practice numerically, but also there you know, okay, I want to keep the S largest to retain the maximum amount of information in the function as possible and to minimize the approximation error. So this is a clean theoretical solution, and this will lead to the so-called, so the accuracy called the best S-term approximation error, where you consider the L2 norm of the tail. Essentially here, all the coefficients that we are not keeping in the sparse approximation, we keep their L2 norm, and this gives you the best S-term approximation error. And there are also theoretical guarantees, and this is, if you want, the first blessing, so to speak, of sparsity. There are formal decay rates for the best S-term approximation error. Really, really elegant theory here. So if you start from the coefficient decay rates, then you can derive convergent rates in S for the best S-term approximation error, and they are mainly of two types. They can be exponential type decay rates or algebraic type decay rates. For the exponential decay rates currently available in the literature, you have a decay with respect to S to 1 over D. So there is a deterioration of this rate for the dimension that goes that goes to infinity. So here we cannot formally consider an infinite amount of variables, for example. However, we still have an exponential convergent rate. For the second family, the algebraic decay rates, we have for fixed D a rate that is lower in S. However, the rate is independent of D. So this allows, for example, to even prove algebraic decay rates for the best S-term approximation error in infinite dimension. So again, this was object of a lot of study in the past decade, and there is a lot of beautiful mathematics being developed here. So we can characterize the best S-term approximation error pretty well, and we know that this choice of S, the multi-index set, is optimal. However, in practice, this still doesn't solve the issue, because how to practically choose this set S will depend on the anisotropy of F. So your function might vary informally, might vary much faster with respect to certain variables than with respect to other variables. And more formally, the decay rate of the coefficients that we have seen in the initial slide is controlled by the size of the Bernstein polyellipse. So the larger the Bernstein polyellipse on certain dimensions, the faster the coefficient decay will be on that direction. So this creates a high, possible very high degree of anisotropy in the function, and as a consequence in the index set S. So now this anisotropy might be known a priori. Maybe in certain application you're able to estimate the anisotropic behavior of S. In this case, you have really, really good methods and well-established methods. For example, you might do interpolation via sparse grids. You can consider quadrature methods. So numerically approximate the integral defining the coefficients, for example, with Monte Carlo integration, or weighted least squares methods. So these are really, really good techniques that can be set up to do high dimensional approximation. However, you need to know your set S that you are trying to produce an approximation in a priori. In the case where this set, and so the anisotropy of F is not known a priori, you might either consider greedy approximation methods, so where the set S is iteratively constructed and enlarged by adding, for example, one index at a time or a set of indices at a time. And this can be very efficient methods, greedy type methods. However, there are no, for general holomorphic functions, there are no theoretical guarantees as of now. There are some theoretical guarantees in the case of parametric PD, for example, if you know that your solution map comes from a specific PD. However, for the general function approximation case, the theory is open. And in this talk, we will focus on the alternative to greedy approximation, which is compressed sensing. So this will be, again, I'm not claiming this is the best method. This will really depend on the context and on how well you can estimate the anisotropy of F a priori. But if you don't know it in advance, I will show you how compressed sensing is a really, really valuable tool that admits formal theoretical guarantees, particular even formally and rigorous convergence rates for approximation in terms of the number of samples.
Hi, I had a quick question.
Yes.
Before you showed like a dimension independent bound, I guess I was wondering if those the class of functions that fit in there are is it practical, like similar to like theorem showed like a dimension independent bound for neural networks, let's say.
First of all, the rate is dimension independent. The constant here of the algebraic rate. So these algebraic type rates are derived by so-called Stechkin type inequalities. And here you do have a dependence on D. However, if you have a suitable restriction on the polyradii and on P, actually, you were gonna need some restriction on P to go to the dimension infinity. You can have a rate that makes sense in infinite dimension, and that can also be, for example, verified. So the assumption, holomorphic assumption, can be verified for infinite dimensional parametric diffusion equations, for example. So there, you can formally prove this.
So in the same spirit, is there some function that we can understand in terms maybe of the operator that produces it that wouldn't fit?
So function that
is there like something that comes from an equation with shock waves, something that comes from
exactly. Exactly. Like, I don't know, if you're dealing with a transport problem, so if the regularity of the solution map is not as high as in the parametric diffusion problem, then this will easily break. Yes. So that's one thing you should be careful with. Yes.
Okay. Thank you.
Yeah, you're welcome. Thank you very much for the questions. Okay, so goal of this talk, as I was telling you, will be studying sparse polynomial approximation methods based on compressed sensing, focusing on the case where the anisotropic behavior of your function is unknown a priori. There's been a past 10 years of activity. There's been a lot of work in the area. This is a subset, a very small subset of all the available literature. Again, in the book, you will find a comprehensive literature review and a description of many variants of compressed sensing methods available. Here I will focus on some recent progress made over the past roughly 4 years, some current work as well, and at the end of the day, at the end of the talk, some open problems. So let me describe the setting. So again, the set S is a priori unknown to us. However, we will for now assume, and you will be thinking, okay, now you might start cheating here. So don't worry about this. I will tell you more about this set in a moment. But we assume to have a large enough set lambda that contains your unknown set S. And I will tell you exactly how to choose this lambda in a moment. But let's assume you know it. You don't know exactly how S looks like, but you know that lives in a large ambient set. Then we perform Monte Carlo sampling. So in particular, we draw our samples, our sampling points uniformly at random according to the orthogonality measure of the orthogonal polynomials. And then, as usual, in approximation methods, we convert this into a linear system. So we evaluate the polynomials. Oh, sorry, this TI should be a YI. Sorry, this is a typo. You evaluate the polynomials and the function at the sampling points, and you end up with a linear system. E here is an error, measurement error, corrupting the measurements, the samples. So in particular, it will contain at the very least a truncation error, because we are truncating our expansion to this large ambient set lambda, but might also include other sources of error, again, like physical noise, numerical error, that might be totally unknown and totally unpredictable. What is the rationale to consider Monte Carlo sampling here? Okay, first of all, we know from high-dimensional integration that the Monte Carlo integration has a convergence rate of order. If you use m samples, you have a convergence rate of order m to the minus a half, which is independent of d. So this is a first good informal argument to suspect that Monte Carlo sampling might be a very good choice. Also, if you know about compressed sensing, you might look at it in a different perspective. The orthogonal polynomial, so the sparsity basis, is made by highly oscillatory functions, so functions that are localized in the frequency domain. So in compressed sensing, from compressed sensing, we know that if you're trying to exploit sparsity in the frequency domain, you should sample in the space domain. And pointwise random evaluations are of course the most possible localized evaluations you can think of. So the uncertainty principle may be another way to think about why Monte Carlo sampling might work. And okay, so let me tell you more about this set lambda. To choose lambda, we will need an additional tool, a definition of so-called lower sets. So a multi-index, polynomial multi-index set is called a lower set if it satisfies this algebraic definition, but without looking at the mathematical definition. Let's focus on the geometrical intuition. A multi-index set is a lower if it has this kind of, for example, here I'm in 2D, if you have this kind of staircase-like behavior. So you don't want to have either bulks in your multi-index sets nor holes in your multi-index sets. And these are, again, widely employed. This definition has been widely employed in approximation theory since, actually, at least since the 50s. And they can reduce the complexity of all possible multi-index sets that you might want to consider. That's the first way to reduce the complexity of the, if you want, of the search space for the optimal set S. But why this structure is a good idea? So first of all, for holomorphic functions, you can formally prove that the best external approximation rates, so the best external approximation in lower sets has the same decay rates as the best external approximation error without the lower set assumption. So if you restrict your polynomial approximation to be supported on a lower set, you can prove exactly the same type of exponential and algebraic decay rates that I was showing you before, with some minor, really minor modifications in the constants. So they're exact, but with exactly the same rates. So that's the first reason. In the case of holomorphic function, we are not losing anything in terms of accuracy if we restrict the search to lower sets. And secondly, even more importantly, in the compressed sensing case, we know what the union of all lower sets looks like. We can exactly characterize this set. This is the hyperbolic cross set. And the nice thing about the hyperbolic cross set is that its cardinality has a controlled growth with respect to S and to the dimension D. Okay, so it's much more lower than, for example, a total degree set, or even worse, a tensor product multi-index set. So just to visualize this idea, this is the hyperbolic cross of order 8 in 2 dimensions. So we know that this contains every possible 9 sparse lower sets. So for example, this vertical lower set, this other kind of staircase lower set, this square-like lower set, and so on. Okay, so we can, and this may be a bit different lower set. So every possible 9 sparse lower set is inside this ambient space. So doing the search inside this hyperbolic cross is good. So we know that we are not excluding any possible lower set from the search. And you see that the degree, the type of anisotropy of the set might be really, really different inside a hyperbolic cross set. You have from a really, really thin line up to a square, so totally isotropic. The range of anisotropy can be really, really as much as you want. And okay, we have defined a linear system. So we would like to minimize the amount of samples that we use. So we would like to use in particular much less samples than the number, than the dimension of this hyperbolic cross that we're going to do the search in. So we're dealing with the compressed sensing problem. We know there are many recovery programs, optimization programs that we can consider. In this talk, we will focus on so-called weighted L1 minimization. So maybe you're already familiar with L1 minimization. Weighted L1 is slightly less popular, but still widely employed in the compressed sensing community. So in this case, the idea is to look for the vector Z that satisfies the constraint coming from a linear system up to a certain tolerance, eta, and we look for the vector. So of course, the system is underdetermined. We have infinitely many solutions. We look for the vector minimizing the weighted L1 norm. Okay, so the weighted L1 is just a variation. We add weights U to the L1 norm. And in this particular case, we will consider a specific choice of weights called intrinsic weights that are defined by the L infinity norm of your polynomials. So they can be explicitly characterized, and there are closed formulas, for example, for Legendre and Chebyshev. You solve this optimization problem, and you have your approximation. Okay, the output of this convex optimization search will constitute will give you the coefficients to your polynomial approximation, and then you have your approximated function. So the blessing of Monte Carlo, if you want, and Monte Carlo and sparsity here actually, a signature result here that was obtained in 2018 by Schiffer, Dexter, Tron, and Webster is about the sampling complexity of this procedure. So Monte Carlo sampling and reconstruction via weighted L1 minimization, you can prove with this setting, and having the weighted L1 norm is really crucial to have such a favorable sampling complexity bound. You can show that the scaling between the number of samples and the target sparsity is only algebraic in S. In particular, the exponent is 2 for Legendre polynomials and log 2 of 3 for Chebyshev polynomials, up to log factors in S. But the good news is that the dependence on the dimension is only logarithmic in D. So if you have this sampling complexity, you can compute an approximation that gives you an approximation error with respect to L2 norm that scales like the best norm approximation in lower sets, even though here we need to consider a slight variation of the best norm approximation error we saw before, because we need to measure this with respect to the weighted L1 norm, plus a truncation error, because we decided to truncate the search over this large lambda, plus this parameter eta. So In this first result, the parameter eta was assumed to be an upper bound to the noise. And then you use this upper bound exactly to set up your optimization program. So this kind of result is really nice in terms of sample complexity and shows us that compressed sensing with weighted L1 minimization is able to substantially lessen the curse of dimensionality because you only pay a logarithmic dependence in D. However, for example, in challenge 3, the fact that data might be corrupted by unknown sources of error, this type of analysis is not entirely satisfactory because we need to know something about the noise, particularly an upper bound to the noise level to set up the optimization. So this is something that we were not happy with, and we started working on a couple of years ago. And this led us to produce a so-called noise blind recovery analysis, or you can even think about recovery under unknown errors. So if you assume you know nothing about the error corrupting the measurements, you can still prove a recovery theorem. So actually, weighted L1 minimization and compressed sensing will still be able to compute a good approximation, but you have a bit more of a complicated error bound here. So if you're trying to estimate the L2 norm, for example, you still have the usual approximation error terms, so best estimate approximation and the linear approximation error given by the truncation. However, now in this new analysis, in this different type of analysis, the role of eta, the new tuning parameter of the weighted L1 minimization and the norm of the noise are disentangled. We assume that maybe you run the convex optimization with a tuning parameter that is not informed by any knowledge of the noise. And then you can still prove this theorem. And we have this extra term. This is interesting because it keeps track of the fact on how suboptimally, in a way, you are mistuning your decoder. So how far is the eta from the norm of the noise? So this also suggests that an optimal tuning strategy for your optimization program in particular, that is when eta is approximately the norm of the noise, not just an upper bound. So if eta is much larger, actually you might lose a lot of accuracy here. So I will not go into any of the technical details here, but I will just say that this kind of analysis is based on a so-called quotient property of compressed sensing proposed by Wojciech in 2010, and then studied later by me and by Adcock in 2018 in the context of L1 minimization. And also a nice feature I was telling you, this to some extent theoretically justifies, for example, something that people were doing practice, that is cross-validation. So try to choose the tuning parameter by estimating as much as accurately as you can the noise of the norm. And this kind of theorem, to some extent, justifies this because we are minimizing this term. So it's good that we can have a recovery theorem that does not rely on any assumption on the noise, which is not realistic. However, the optimal tuning still depends on the noise. So we were not happy with this, and we decided to consider two alternative decoders to see if the situation could be improved.
Could I ask a quick question about the last theorem?
Yeah, sorry.
Here the lambda set that you're constraining to is going to be some hyperbolic cross that contains whatever the lower set, the sort of worst case lower set is that you're working in.
Yeah.
Okay.
Yes. Yes. There's good. Yes.
So lambda could still be sort of large, the total basis that you need to consider.
Yes. Yeah. So the total search space will be the largest dimension we're going to consider. That's going to be the number of unknowns in our convex optimization problem, and this can be large scale, not scaling like algebraically in S. Sorry, not independent on D. Scaling algebraically in S, but not being independent on D, unfortunately. So yeah, that is exactly it.
That's okay. Yep, just checking. Thanks.
Yeah. Okay. So we considered two other alternatives to the optimization problem I showed you before, that is called quadratically constrained basis pursuit. Particular two unconstrained versions of weighted L1. One is the weighted lasso, one is weighted square lasso. So the first one, at least in the unweighted version, is really, really popular in statistics and computer sensing. It was proposed by Shirani in the 90s. The second one is also quite popular in statistics. However, it doesn't look to be as widely employed in computer sensing and in functional approximation. Now this is changing in the past few years, but I will show you why this different type of decoder has really, really nice features when it comes to dealing with unknown errors. So the standard lasso has this data fidelity term that is the L2 norm squared of the residual plus a regularization term, which is the weighted L1 regularization. The square lasso, it's really it's different from the lasso in a tiny aspect. You just remove this exponent too. Okay, so we consider only the L2 norm of the data fidelity term, and this might seem like a small deal, but however, this leads to a substantial difference in terms of recovery guarantees, because you can prove again recovery guarantees for weighted L1 minimization for these two decoders in the context of high-dimensional approximation, and you will have the same approximation errors as before, plus the unknown error. And the theory still suggests optimal tuning strategies for these two different decoders. And in the case of the lasso, the optimal tuning strategy depends on both S and the norm of the noise. So we still have this suboptimal feature. However, in the square lasso, the really attractive feature of this decoder is that the optimal tuning strategy only depends on S. It is independent on the norm of the noise. So we were really happy when we discovered this. Again, this is well known in statistics, but was not employed and used in computer sensing for some reason. But this is a really nice feature of this optimization problem. And it can also be verified in practice. So this independence of the optimal tuning on the optimal tuning strategy on the noise. So I will not say much here because time is flying, but essentially you can plot the recovery error as a function of the tuning parameter for the three different decoders, like quadratic constraint basis pursuit, lasso, square lasso. And you will observe for different noise levels injected into the measurements, you will observe every time a local minimum that corresponds to the optimal choice of the tuning parameter. And these local minima are shifted for the first two decoders, quadratic constraint basis pursuit and lasso. However, you can see that also numerically, you can observe they are aligned for the square lasso. So they're independent on the color, and here the color is the amount of noise we are injecting in the measurements. And so again, this can be nicely validated. It's not just a theoretical, nice device, but also it can give you practical benefits. Okay, so all this theory is nice. It tells us error bounds that depend on the best system approximation error in lower sets, plus a truncation error in the ambient set, like the hyperbolic cross. So still, this doesn't precisely provide a convergence theorem for computer sensing. So the question is, can we actually prove, given a certain budget of samples M, can we prove a convergence theorem for computer sensing? So can we show that the error decays at a certain rate depending on the budget of samples M? So this turns out to be possible, and you can achieve almost the same rates as those for the best S-term approximation error. So this result is kind of partially informally stated here and will be in the book. Part of this result is already published, especially for the Legendre case, is already published in a paper in collaboration with Menadkov, Nick Dexter, and Sebastian Moraga. But so this is what happens here. if you have a fixed number of budget of samples, you define this m tilde, which somehow plays the role of the target sparsity S. So you divide by the log factors in the sampling complexity rate. And for example, here for simplicity, if we focus on the noiseless case, you can achieve exactly the same type of either exponential convergence rates in m, this new parameter m tilde that is really close to m up to log factors, or algebraic type convergence rates. So, and this provides a full convergence, so a kind of a clean convergence theorem for compressed sensing in high-dimensional approximation. A couple of remarks. Choosing the square root lasso here is really crucial because when proving this kind of theorems, you need to deal with the fact that the truncation error is unknown, and so you don't want the tuning parameter to depend on this unknown error. And using the square root lasso is crucial here. Moreover, you can also have a noisy version of this result. You can allow noise in the measurements, and you will have exponential decay rate plus a noise, the usual L2 norm of the noise. So that's not a big deal, that can be done. Another extension related to the challenges I was talking about at the very beginning is the extension to Hilbert-valued functions. So now this could also be done. You can extend the approximation framework via compressed sensing to the case where the output is an element of a Hilbert space. So this was initially proposed in 2018 in the context of so-called simultaneous compressed sensing, where only L1 minimization was used, but then you can actually adapt all the framework based on weighted L1 and square root lasso to the Hilbert-valued case. In this case, you just need to be careful. Your polynomial expansion, so V is the output space, and let's say it's a separable Hilbert space. Your coefficients are element of a Hilbert space. And so here, all the definition of the square root lasso, for example, you should replace the absolute value of the entries of your vector with the norms in this Hilbert space you're considering, V. But you can formulate a square root lasso type optimization problem in this case as well. So now this looks a bit abstract because we have this V norm here, but you can make it in a way purely numerical by considering a subspace of your Hilbert space, finite dimensional subspace of your Hilbert space, and expanding into components with respect to a certain basis there. So you can reformulate the square lasso as a similar convex optimization problem that only depends on this now scalar coefficients. Okay, so you can have a fully implementable convex optimization problem, and you can also prove the same type of scalar, the same type of convergence rates as in the scalar valued case. You just need to be careful because instead of Lebesgue spaces, now you're dealing with Lebesgue-Bochner spaces. Okay, here, for example, this is a Bochner integral, but it's not a big headache. So all the theory nicely generalizes to this setting as well. Okay, so this leads me to the last part of the talk before the open problems. That is the the deep neural network approximation. So how can we use what we know about sparse polynomial approximation in a deep neural network context? Try to be as fast as possible. I know time is flying. Okay, I don't need to motivate probably to this audience why neural networks are really popular. They led to many breakthroughs in computer vision, text processing, and so on, and they're becoming increasingly popular in uncertainty quantification, or for example, discovering unknown dynamical systems, or even being used in numerical PDE solvers. So they're being increasingly popular in scientific computing and computational math in general. And there is, so this popularity essentially caused a lot of activity in terms of deep neural network approximation theory results. So there is a variety of really, really nice results that can show you that you can approximate functions in certain function classes up to arbitrary accuracy with neural networks, for example, in classes like Sobolev spaces, piecewise smooth functions, and so on. In particular, there are also results for holomorphic functions, like the functions of interest that we are considering. However, all these theoretical approximation theory, this approximation theory results, they deal with the existence of a neural network that is able to accurately approximate the whole class, but they do not tell you anything about how to train such a neural network, for example, or how many samples do you need to train this neural net, to find this neural network and accurately compute it. So these questions led to considering this problem from a theoretical perspective and try to see if we can give an answer. So the setting is the following here. Again, let's say we are in the Hilbert-valued setting. Then your function can be, again, you consider a finite dimensional subspace of your Hilbert space and an orthogonal projection onto it. And you can expand. Now, be careful here. I'm not expanding with respect to the orthogonal polynomials, but I'm expanding with respect to the basis of the output Hilbert space. Then you're going to have some coefficients that depend on the input variable. And so the goal now is to approximate. These are in turns scalar high-dimensional functions. So the objective now is to approximate these scalar valued functions. And this might be done with a deep neural network, for example. Here we're just considering standard feed-forward deep neural network that are composed by, constructed by a composition of affine mappings and nonlinear activation. For example, the so-called rectifier linear unit. Again, I'm not giving you any details here, but hopefully in this audience you are already familiar with neural networks. And we want to approximate these coefficients here with this network that we're looking for. And it's possible to do this and to have the following type of guarantee. So we call this as a practical existence theorem, because it doesn't only tell you about the existence of a neural network that is able to approximate holomorphic functions, but also tells you that this neural network can be computed by optimizing a certain training procedure. So the result assumes uniform sampling, like Monte Carlo sampling, like in the polynomial approximation case. And you can prove that there exists a class of ReLU deep neural networks whose architecture can be characterized. So the depth and the width of such networks can be explicitly bounded in terms of this M tilde. There's also a regularization functional that is equal to a certain norm of the trainable parameters of this class of networks, such that if you compute a minimizer to this particular optimization program that resembles somehow, as you can see, the square root lasso, because there is a square root here in the data fidelity term, then if you're able to compute such a network, and this network is able to achieve the same exponential convergence rates as those for sparse polynomial approximation via contrast sensing. So here, the real statement is really long. I encourage you to check out our recent paper in collaboration with Ben Alcock, Nick Dexter, and Sebastian Moraga for the full details. But that's the summary of this result. Now there is a little caveat here. This training procedure is not entirely standard. Particularly, we assume to have this proof, we assume that only the last layer of parameters is trainable, which does not correspond with people usually doing practice. But nonetheless, this is the first result that exhibits a concrete training strategy to find a network with optimal approximation properties. Okay, there was a sketch of the proof, but I will skip this because I'm really running short of time. So let me conclude with a few open problems and what I think are good research opportunities in the area. So for the sparse polynomial approximation case, a crucial open question is the sampling complexity optimal? So the scaling in particular the algebraic scaling as to the lambda, is it optimal, or can we make it linear, like in standard compressed sensing? That would be really nice. As of now, it's possible to have a linear in S rate only for Chebyshev polynomials and for in the asymptotic regime for asymptotically large S. That's the only case where you can observe a linear dependence in S. Otherwise, this is it's not clear if it's possible to achieve such linear scaling in the generic Legendre-Chebyshev setting. Also, another going back to the comment by Mark before, the convex search is done over the hyperbolic cross set, and this has a dimension n. Then for really large scale problems, this can become a computational bottleneck. So although in the sample complexity, this kind of methods can substantially lessen the curves of dimensionality, in terms of reconstruction time, the challenge is still there. So there's still work to be done. I think a really promising direction here is to understand if these techniques can be combined with sublinear time algorithms, such as those proposed by Mark and his collaborators. The key question is, can we have a sublinear algorithm while preserving a good sampling complexity that doesn't scale too badly in S? And also, I'm personally curious to see, and maybe someone in the audience has some idea. So usually when we deal with holomorphic regularity assumption, there's a lot of literature showing that this holomorphic assumption is true for parametric differential equations, like again, diffusion equation, heat equation, harmonic oscillator, initial value problem. There are really large, or you can parameterize the domain, for example. There are many types of parametric dependence that give you a holomorphic function. However, can we, I wonder if we can verify this in other different type of models. So if anyone in the audience has know about results in this direction, I would be really, really interested in talking with them. This would be a nice way to have formal recovery guarantees to other type of applications that do not necessarily deal with differential equations. And for deep neural networks, I would say there are many, many open questions. So like beyond the practical existence theorem, there are totally open questions like how to optimally design the architecture, if it's possible to improve the sampling strategy, or how to make the practical existence theorem more realistic. Like, for example, where all the parameters of the network are assumed to be trained. Let me also talk about an opportunity. So you might have understood that I'm a big fan of the square lasso, and I'm trying to promote it as much as possible. And I want to tell you that so the square lasso is not only useful in function approximation, it was also recently used in the context of compressive imaging, for example, when dealing with the problem of optimal Fourier sampling strategies, or also in deep neural network signal reconstruction for the design of networks that that have improved stability properties. Again, basing all these designing algorithms based on the square lasso can be very beneficial if you're dealing with stability issues. So I think here there is a good opportunity to look for contexts where maybe robust sparse regularization is needed, and where the nice properties of the square lasso could be useful. And finally, as a final extension, I would like to mention this talk. I mentioned some PDE problems, but the PDE solver was always a black box. So it turns out that you can also use compressed sensing to solve a PDE. So inside the black box, I will not tell you anything about this, but I've done some work in the past years with some collaborators in Italy here from Politecnico di Milano and University of Pavia to see how to use compressed sensing in different PDE methods, like Petrov-Galerkin, spectral collocation, isogeometric analysis. And I think an interesting question here is, can we use this sparse polynomial approximation methods via compressed sensing in the context of PDEs? So like for solving high dimensional PDEs. Also, is it possible, many people are using deep neural networks to solve PDEs. So is it possible to prove a practical existence theorems for deep networks in the context of PDE solvers? That's another question I will be really, really curious to see answered. So this is it. Thank you very much for your attention. Sorry for if this took a bit longer than expected. So again, I remind you about the book, and this is a bunch of papers you might want to look at if you're interested in what I was talking about. And if you're looking for postdoc and you were not here at the beginning, I'm still considering applications for this opening that I have in my group. So if you like this research area, please send me an email. Okay, thank you.
Thanks a lot. Excellent. So I will open up the floor to any questions that anybody might have and didn't ask during the talk.